So we're going to be talking about gases. We went over different physical states for matter. Matter can be classified depending on the physical state, which means that you can have, for the most part, solids, liquids, and gases depending on pressure and temperature. And we can also classify matter depending on the composition, which is where we have elements, compounds, mixtures, like pure substances versus mixtures. So we're going to be focusing now on that physical state, gases. So some properties for gases, they don't have a defined shape or volume, and they are compressible. Okay? So gases, they have in common with liquid that property of not having a definite shape. And gases are compressible, okay? And that means that when you change the pressure, you can change the volume. If you increase the pressure, you're going to decrease the volume of a gas sample. And that is possible because there's a lot of space between the particles in a gas. Okay? If you have particles, a collection of particles in a gas sample, they have a lot of space between them, so you can actually apply the pressure and force those particles to get closer to each other. That's what compressible means. So the volume of a gas, it's affected significantly by changes in pressure and in temperature, and we're going to see that in more detail soon. And in comparison to liquids and solids, gases have very low density values. And then we have the kinetic molecular theory, which explains the behavior of gases, or the behavior of gases. It's what it's used to write down these postulates that we have here. Gas particles feel no attraction for each other, so we are going to assume that that's 100% true for the most part of our discussion. Then we will see at some point that that is not always true. But if there's no attraction between the particles in a gas, your particles, they're going to be moving freely. That's why they occupy all the space that you provide them. If you have a gas trapped into a small container, let's say like a 2-liter container, and you transfer your gas sample to a 10 liters container, your gas sample is going to expand and it's going to occupy the whole container, because the particles in a gas, they feel no attraction for each other. The kinetic energy, or the energy of motion for your gas particles, is proportional to the temperature. As the temperature increases, so does the energy of your gas particle. And then everything that we're going to be talking about gases, all the properties, we can describe using four different measurements: pressure, volume, temperature, and amount of gas. And we're going to see the relationship between all of them. Okay? So I'm going to talk a little bit about pressure before we move to something else. Pressure, it's a force. It's a force per unit of area. Now, you need to think about gas particles moving all the time. If you have a gas trapped in a container, your gas particles, even if you cannot see them, they are moving and colliding with the walls of your container constantly. Those collisions between your gas particles and the walls of the container, it's what is going to cause a pressure, because they're colliding with the force in a specific area, giving you a pressure. That's the result of your collisions with the walls of the container. We have different units to express pressure depending on the instrument that it's being used and for what you're using the measurement for pressure. We have millimeters of mercury, torrs, pounds per square inch, atmospheres, and we have the Pascal here, which is the unit of pressure in the International System of Units. And then down here I have the relationship between all of your different units, or not all of them, but some of them. So we can convert units of pressure using this here as conversion factors. For our calculations, the most common units of pressure are millimeters of mercury, torrs, and atmospheres. So I'm going to show you how to do one conversion here using the information that you have, and then you can solve the other one. Calculator. So first of all, the number that it's given, it's in units of ATM or atmospheres, and you're trying to get your millimeters of mercury. So you need a conversion factor that relates your atmospheres with millimeters of mercury, and you have that 1 atmosphere is the same to 760 millimeters of mercury. So this is your conversion factor. 1 ATM equals 760 millimeters of mercury. So if you have 1.08 ATM, how many millimeters of mercury you have? So I'm going to write down my given number with the given unit, and I'm going to write down my conversion factor with the unit that you're trying to get, which is the millimeters of mercury on top, and the unit that you're trying to cancel out, which is the ATM on the bottom part. And I'm going to use my numbers here to fill my conversion factor. I have, with my millimeters of mercury, I have 760. And with my ATM, I have 1. And that's giving you 821. So if you have 1 ATM, that's the same as having 760 millimeters of mercury. But if you have 1.08 ATMs, you're going to have 821 millimeters of mercury. So for the second one, you need conversion factor between ATMs and PSI, which is your pounds per square inch. 1 ATM equals 14.7 PSI. This is 2 significant figures, so I'm going to write down your answer in 2 significant figures. That should give you 14 PSI. So we have these 4 properties that we're going to use to describe gases. We have volume, pressure, temperature, and amount of gas. Okay? So we have simple gas laws that relates 2 specific properties. So they look at the relationship between 2 specific properties when the other 2 out of the 4 are kept constant. Okay? So the first one, Boyle's law, is the relationship between pressure and volume. If you're looking at the relationship between pressure and volume, you need to keep the amount of gas and the temperature constant. Because if you change the amount of gas, that's also going to affect the volume and the pressure. If you change the temperature, that's going to affect the volume and the pressure. So to avoid changes in the relationship that you're trying to study, you're going to keep two of them constant, and you're going to look at what's happening to the pressure if you change the volume, or what happens to the volume if you change the pressure. So Boyle's law, pressure and volume keeping constant amount of gas and temperature. Now, a law, it's usually a mathematical equation that explains the behavior of something. So we have here Boyle's law. We have pressure, volume equals pressure and volume. 1 and 2 means that you have your gas sample in an initial state. So you have an initial pressure with an initial volume. Something changed. You can change the pressure or the volume, and you're going to have now a new state. So I have here two containers. Container on the left, container on the right. What is different between these two is just the size. You have 10 dots in this one, 10 dots in this one. Each dot represents a particle, a gas particle. So the amount of gas is the same, and let's assume that this is at room temperature and the temperature for both is the same. What is constant is amount and temperature. If pressure is it's a force, right, and it depends on the number of collisions per area, you have the same number of particles of gas in both containers, but the pressure is not going to be the same because your number of collisions is going to be higher in this one right here. If you have a bigger space or a bigger volume, which is what we're comparing, if you have a bigger volume, your gas particles, they have a bigger amount of space to move around, which means that the number of collisions is going to be lower because you have a bigger container. When your container is smaller, like in this one, the one on the left, right, you have higher chances of your particles of gas to move around and collide with the walls of the container than what you have for this one. Since you have a smaller space here, you're going to have a higher number of collisions, which means that you're going to have a higher pressure. So smaller volume, higher number of collisions because your particles are going to collide with the walls of your container more often, and those collisions are the ones that are responsible for producing a pressure in your container. Okay? So smaller volume, higher number of collisions, higher the pressure. Okay, that's what's happening here when you're comparing two gas samples in containers with different sizes. So we can write down the relationship between pressure and volume just looking at this right here. Inversely proportional, okay? Which means that if you're increasing the volume, the pressure is decreasing. If you're decreasing the volume, the pressure is increasing. Inversely proportional. If one is increasing, the other one is doing the opposite. Now I have here a problem where you have to apply your Boyle's law. Okay? Now in your equation, you have four things. Usually in this type of problems, you're going to be given 3 out of the 4. So you need to solve your equation for that fourth one that you're trying to calculate. My recommendation for solving these problems, first of all, you need to identify what you have. Second, you need to predict what you are expecting based on the relationship that you have for these properties. So let me check what you have, and then we can go over what I just said. Looking at the units without even looking at the problem, that's for ATM, that's a pressure. And that's liters right there, that's a volume. So you have a container that has a movable piston, something that can move up or down. You can think about a syringe. Okay, if you have a syringe that it's sealed, okay, that represents a container with a piston. That plunger, it will be like a piston in your container. So you have your gas sample in that container, and you have an initial volume. You have 6 liters is the volume for your container, which means that that's the volume of the gas sample that you have. And you have that volume when the pressure applied to that piston, it's 4 atms. Now, this is what's happening. Your pressure is changing from 4 to 1. So what's happening to your volume? So I'm underlining your numbers in 2 different colors. I have 4 atm and 6 liters in purple, because those two represent my initial state. I have my gas sample occupying 6 liters when the pressure is 4. And then the pressure is going down from 4 to 1 atm. And you need to find out what volume do you have now when the pressure is 1 atm. So I'm going to write down my equation. You have this part of your equation, initial and initial. Your initial pressure, your initial volume. You have a final pressure, and you're trying to find your final volume. So my first suggestion is to find out your numbers, what they represent. Second is to make a prediction. Making a prediction means you have your initial pressure of 4, your volume of 6, and your final pressure is 1. Your pressure is going from 4 to 1, which means that the pressure is decreasing. Volume and pressure are inversely proportional. So if the pressure is decreasing because it's going from 4 to 1, it means that pressure is decreasing and the volume should be increasing. You're calculating your volume because you have all the numbers that you need to get a volume when the pressure is 1. But you should know before doing the calculation that your volume has to be a number that is bigger than 6 liters, because if the pressure is going down, the volume is going up. So let's put everything in your equation. If you're trying to get V2, P1, initial states, final. You're solving this equation for B2. So you need to divide everything by P2. So that cancels out from that side. And you're getting that V2 is your P1 times V1 divided by P2. Initial pressure is 4 atm. Initial volume is 6 liters. And your final pressure is 1 atm. That's going to give you 24 liters. Your final pressure is smaller than your initial pressure, which means that your final volume has to be bigger than your initial volume, and all of that is true. Your final pressure is 1, your initial pressure is 4, bigger than 1. Your final volume is 24, bigger than your initial volume, which was 6 liters. So this is an example of Boyle's law, relationship between pressure and volume. Pressure and volume, they are inversely proportional. Now we have the second simple gas law, which is the relationship between volume and temperature. And the temperature is in kelvins. Relationship between volume and temperature, it's given by Charles' law. If you're looking at the relationship between volume and temperature, you need to keep constant the amount of gas and the pressure. Out of the 4, you're looking at the relationship between 2, and the other 2 are kept constant. Now I have my container here, and you should think about this top part here as something that can move up or down depending on what I'm doing to the temperature. So I have my gas sample in there. I have 10 particles and 10 particles. And now I'm going to say that I'm going to increase the temperature of my gas sample. So increasing the temperature is going to make your volume increase also. Volume and temperature are proportional. Which means that if one is increasing, the other one is also increasing. And it works the other way around too. If you increase the temperature of your gas sample here, your gas is going to expand, occupying a bigger volume. And we have an equation that relates your volume and the temperature right here. This is the equation that we have for Charles' law, which is going to be used whenever you have to check the relationship between volume and temperature. So you have something similar to your Boyle's law. You have an initial state and a final state. So you're usually given 3 out of the 4, and you're finding the 4th one. Important things. Whenever you have a problem involving temperature, your value of temperature needs to be in kelvins. The unit for your numerical value has to be kelvins. So just in case, I'm writing here the equation to convert your Celsius to kelvins. If you have a temperature in Celsius, you need to add 273 to get your kelvins. So I have a problem down here. And in your problem, let's identify what you have. You have 2 values of temperature, you have 1 value of volume. Units of milliliters, units of Celsius for these 2. So 2 temperatures, 1 volume, and you're trying to find a volume. So you have a sample of gas. You have your volume, and that sample of gas, it's in a container at this temperature right here. So this is your initial volume, and that's your initial temperature. And then the problem is telling you, okay, you have your initial sample at 22 Celsius, and you can use my example here because it's the same thing that's happening here. You have your initial volume of 48.3 at 22, and you're increasing the temperature to 87. So it's going from 22 to 87. That's your final temperature. Okay? And you want to know, okay, if when the temperature is 22, I have this volume, what volume do I have if the temperature is going from 22 to 87? So you're solving for your V2 right here. But before getting your numbers, let's predict what's going to happen. If the temperature is increasing, I already told you, relationship between volume and temperature, it's proportional. So if one is increasing, the other one will be increasing also. So if the temperature is going up, your volume has to go up also. So you're expecting that the number that you're calculating here for your volume, it has to be a number that is bigger than your initial volume of 48.3. So let's write down the equation. Oh, let's do something before writing down the equation, because you need your temperatures in kelvins. So you need to convert your Celsius to kelvins. So there's a reason why we don't use the Celsius in our calculations. First of all, when we use kelvins, there are no negative numbers, no negative temperatures in kelvins. And also, at some point, we're going to use a constant. And the units in that constant, the unit for temperature in your constant is given in kelvins. So if you have a temperature in kelvins, you can actually cancel out your unit with the unit that you have in your constant that it's also in kelvins. So we have the temperatures now in kelvins, and now I can solve your equation for what you're trying to get. This is your equation, and you're trying to get your volume right here. The final volume at the new temperature from 22 to 87, your new volume. So to get volume, you need to multiply times T2 on both sides. So you can cancel that and you can get just your V2. So T2 times V1 divided by your T1. So I have my T2 is 360 kelvins times your initial volume 48.3 milliliters divided by your initial temperature of 295 kelvins. So units that are canceling out, it's unit of temperature because you're trying to calculate a volume. That's your volume 2. And that will be 360 times 48.3 divided by 295, 58.9. And that's milliliters. And that's your volume 2. Your volume 2 is bigger than your volume 1 because your temperature 2 is bigger than your initial temperature. They are proportional, so if one is increasing, the other one is increasing. Temperature 2, which is your final temperature, is bigger than your initial temperature. So the volume that you're calculating has to be bigger than your initial volume. And then we have the last one. This is the last one that we have for the simple gas law out of the three. Avogadro's law is the relationship between volume and amount of gas. And actually, this is the easiest one for you to visualize. If you increase the amount of gas, the volume is going to increase, right? You're adding more of something, so the volume will increase. If we're looking at the relationship between amount of gas and volume, out of the four properties that we have, if we're looking at the relationship between two of them, the other two need to be constant. So we're keeping constant temperature and pressure for this example here. So I'm going to go over the calculation and I'm going to show you with my diagram, but I'm going to do both things at the same time. We have our equation right here. The equation for Avogadro's law, the relationship between the volume and amount of gas. So in my problem, I have a balloon with 0.158 moles of gas. So this is my initial right there. I have 0.158 moles of gas, and my volume is 2.46 liters. Now you know the relationship between amount of gas and volume. If you increase the amount, the volume is going to increase. Right? The more you have of something, the bigger it will become. So I'm going to add in my balloon, I have an initial 0.158 moles of gas, and the problem is telling you an additional 0.113 moles of gas is added. Okay? It's not that your number of moles is going from 0.158 to 0.113. To the number of moles that you have in your balloon, you're adding now 0.113 moles. So if you're adding more gas in your balloon, it means that the size of your balloon is going to increase. So now in here, you don't have 0.158 moles of gas. You don't have 0.113. You have the addition of those two amounts because you're adding on top of the amount that you had, you're adding this many moles. So you need to add them to actually get how many moles of gas if you have in your balloon. And what you need to find out is your new volume. That's what you need to calculate. When you had 0.158, your volume was 2.46 liters. Now you're adding on top of your initial amount this many moles of gas. So you're going to have a new volume, which is going to be a bigger volume because you're adding more gas. So let's calculate what's the final volume. So your equation is V1 and 1 equals V2 and 2. And we're solving for volume again. So to get rid of N2, you need to multiply N2 on both sides. And that's going to give you your equation to find out your volume 2, which is going to be V1 times N2 over N1. Your volume 1 is 2.46 liters times your final number of moles, which is 0.271 moles, which is the addition of the two amounts that you have. Your 0.158 initial amount plus whatever you're adding, which in this case is your 0.113, divided by your initial amount, which was your 0.158 moles. Moles cancel out with moles, and you're getting a number in units of liters, which is what you're trying to calculate, a volume. 2.46 times 0.271 divided by 0.158, and that's going to give you 4.22. Three significant figures, 4.22 liters. So we went over some properties for gases, kinetic molecular theory for gases, different statements in there. Okay? We talk about pressure, how to convert unit of pressures if you have ATM to go to millimeters of mercury or the other way around. And we went over the three simple gas laws, Boyle's, Charles, and Avogadro's. All of them looking at the relationship between the volume and other properties like pressure, amount of gas, and temperature. So now I'm going to flip the page so you can work on some problems that I have here. I have your problem and the answers for them. You should solve your problem and you should check your answers with the answers that I'm giving you here.